Good morning. A warm welcome, colleague architects, architects in SPE, professors, Switch2Save, project partners, and all interested in an energy-efficient building sector. The next 90 minutes, we will have our Switch2Save training event with some very interesting presentations about smart glazing and the Switch2Save project itself. At the end of this training event, we will launch the competition, the Switch2Save architectural design competition. And I'm happy we have already quite some participants. The event will be recorded. This is important. And the recording will be available on the website for all the students and architects interested in participating in the competition. I'm happy to announce our first speaker. This is Paul Carteuvels. He will speak about the European strategy for energy efficient buildings and the Green Deal objectives. Paul Carteuvels is the executive director of Bouygues Europe, which is in charge of relations with European institutions in Brussels. This French-based Bouygues group is active worldwide in the construction sector and in France also in telecom and audiovisual sector. But more important here today, Paul is the president of ECTP, the European Construction Technology Platform. And this platform gathers actors from across the construction sector value chain. ECTP is also co-chair of the World Green Building Council, of the Build for People partnership with Horizon Europe. So really the link between European research and the building sector. I give you the floor, Paul, please.
Good morning to all of you present live today, and hello to those who will follow this later on online also. So I've been asked to tell you about what is happening in Brussels for the moment around energy efficiency, the Green Deal, etc. So I will take a few minutes to tell you the many initiatives on the issue that are happening for the moment. First of all, to start from the global context, the famous Green Deal. To make it short, I found a way to say what the Green Deal is in a short way is to come back to an older expression called the sustainable development, which we don't use that much anymore. And if you remember, sustainable development had three pillars, which were the economic, environmental, and social pillars. Well, the Green Deal is the sustainable development three pillars plus a climate pillar. That's the best way to summarize in a very short way what is behind the Green Deal. This climate pillar, of course, takes enormous importance. You probably also know that the Commission has fixed very ambitious objectives to reduce CO2 emissions. There is this number of minus 55% of CO2 by 2030, reference base 1990, and CO2 neutrality by 2050. So what I can synthesize from this is that the Commission wants to go faster than the Paris Agreement. This is really important. It has been pushing it much further. To reach this, the Commission put a very strong pressure on renovation. Some of you probably heard that was launched a renovation wave action plan from the Commission. The objective is to renovate fasten by 2 times the renovation rate until 2030. So renovation is going to be the subject. It's not an easy one, but I mean, the Commission is really putting the pressure on this renovation aspect. Another thing that you know well is, of course, Horizon Europe, former Horizon 2020. You know that Switch2Save is part of the energy efficient building PPP of Horizon 2020. It's continuing. So you know that regarding innovation, ECTP has been the partner of the Commission since 2010 already. And for the 10 past years, the focus was on energy efficient buildings. Now with the new partnership, Build for People, it extends to all dimensions of construction, not only that aspect, but it remains a key aspect. The objective is to make sure that every year we have projects proposed by the Commission in our construction system. You have to realize that 10 years ago, 12 years ago, we were wondering every year, are we going to have a certain number of projects on construction and in energy efficiency? We never knew. So the relationship allowed to create a stable flow of projects around energy efficiency in particular. That's for the innovation part. In December, that's an aspect that probably you don't follow that closely. There was also a regulation proposal, a directive proposal, so regulatory work is the Energy Performance of Buildings Directive to be reviewed. The text was adopted quite recently, so the Commission is really putting the pressure by reviewing its legislation really fast to put the pressure. And what they expect is that new buildings should be zero emissions by 2030. They also want, of course, more renovation, better energy performance certificates, etc., etc. So these EPBD, as you call it, European Energy Performance Building Directive, is a key dimension of the legislation. Something more nicer for the architects, probably you know it better than I do, is the new Bauhaus initiative. That the new European Bauhaus, I guess you all know about this. I think it's a beautiful one. Also because now it brings what you will like is not only the usefulness, but also the aesthetics and the relationship with the people, the quality of life in the city. So the new European Bauhaus, I hope you're all in a way or another involved, at least receiving the news from the initiative. Otherwise, I insist that you take good attention at the NEB. There was a report end of last year on the relationship between innovation and the new European Bauhaus. I did not have the time yet to read it, but I'm planning to. But I draw your attention to this. There are certainly elements that could be useful to you. I would like also to tell you about something a bit different that you probably did not hear, but is also important. As I told you before that the Commission wants to go faster than Paris, the Commission also wants to look not only at CO2, not only at energy efficiency and clean energy issues. This is really important because if you want all the projects that you will work on to be more accepted, more attractive, you have to realize that the Commission now, climate-wise, has two objectives. CO2 objective is called the climate change mitigation. That's the expression to say we try to reduce the CO2. But the Commission also said climate change adaptation needs to be put forward with a lot of priority. And I think the climate events of those last months show you that indeed, when people have been flooded, they probably have other issues than CO2 before rebuilding or protecting their houses also. So climate change mitigation and climate change adaptation and architecture in those two aspects is totally concerned. But you also have environmental objectives that are really connected. The Commission says we want that European finance goes to projects and activities that have these climate objectives, but also environmental objectives. And this is the water management, the circular economy principles, the pollution control, and biodiversity. So remember, water, circular, pollution, biodiversity. Those four aspects have to be there if you want to attract finance. So you see that the situation has become much more complex. We need to look at these 6 objectives also. It's called the taxonomy. Just you hear the word. It's a very complicated regulation being adopted for the moment. It's a nightmare for everybody, but the 6 objectives make sense. And you need to have that in mind when you think about your future buildings. I think it's really important. Just to complete this overview of the initiatives of the Commission, because my timing is running out, I wanted also to remind you architecture-wise how it is important to not only do the high-tech stuff, because you're totally in the high-tech stuff, but keep an eye on traditional solutions. Keep an eye on what people have done before electricity to make sure that buildings would be as best as they could for energy efficiency. It's really important to look at that. It can be the orientation of the building. It can be, of course, the natural lighting, the bioclimatic architecture, as we call it. Vernacular architecture is the ancient architecture. And biomimicry, try to imitate nature. More use of the solar thermal power, because we all talk about PV, but not enough about solar thermal. So all those aspects of older solution could be mixed with the high-tech solution. I think this is important. If we have a blackout, we need to make sure that things get as best as they can, even in a blackout situation. I insist also on materials. You are on some part of the materials, of course, already in your project here. So look at all the things materials can do in this energy efficiency principle. So you see, keep your eyes wide open, because you have to bring together many solutions. And to conclude, if you did not have the chance to see the Bauhaus Museum in Berlin, please go and visit it, because this new European Bauhaus has a meaning. There is a museum in Berlin that I saw when I was a student myself, when I was 23, when I saw that, a long time ago. And it's a museum of inspiration. Really, there is a lot of ideas, not only in architecture, also in furniture, whatever. So this Bauhaus Museum is really very inspiring. If you have a chance to visit, if you did not, please do. And I finish. I think it's my timing is over, and I thank you all for the attention.
Sarah, we can't hear you.
Sorry, yes, now it should be better. Thank you, Paul. You gave a very interesting introduction and an update on what's happening at European level. And not to forget the Bauhaus, which we all welcomed, of course, as architects. I would also ask the participants to raise their hands virtually if there are any questions for Mr. Karteuvels. He is here to answer them. If not, raise your hand and we can, after the next speaker, also have a Q&A. So now I would like to invite the coordinator of the project, John Faulte, to speak about Switch2Save. You probably never have heard about it. John graduated from the University of Leipzig with a diploma in physics, and he is now a research group leader for roll-to-roll vacuum coating technologies in the business unit plasma technology at Fraunhofer FEP. I give you the floor, John.
So, Sarah, thank you very much for the introduction. And Paul, also to you, thank you very, very much for the great insight on what are the ideas, what are the objectives of the European Commission in this sense, because this is really important and really interesting. And by the way, I'm coming from the Bauhaus city Dessau. I've lived there 18 years, so I know a lot about this. And it's very interesting to see how you practically can be energy efficient just by some design aspects and some things that bring, of course, other challenges. And the Switch2Save project is dealing with such challenges. The Switch2Save project has been funded in Horizon 2020. As we are all now at the halftime of the project. And we are dealing with an interesting aspect of buildings that have large windows and large glass facades that you'll see in a lot of office buildings these days. But you also see it in single-family homes. We have built our single-family home in 2014, and we have a lot of large windows towards the south. And those are some good things, because in winter you probably can use the radiation heat of the sun, but in summer you will get some trouble. And I've taken here a scientific publication as a starting point. What they did, they are not from Europe, but it's practically similar to other studies done in Europe. What they did is they calculated the energy demand for heating and cooling in dependence on how large the windows in a building are. And they found out that the windows, if you increase the size of the windows to the certain orientation, west, east, north, and south, you will have some influence on the heating energy demand. But you have much, much bigger influence on the cooling energy demand. You can save some energy from 16 to 14 kilowatt hours per square meter with a large window to the south, but you will increase the cooling energy demand with the same window oriented to the southwards. And it's even worse for east and west. Why? Because the sun is having a lower angle and can directly shine into the window and into the building. The important aspect, important message I want to give you for this project, and I want to give you from these slides, that if you have high window to wall ratios, if you have large windows with large glass facades, you will find yourself in a situation that the cooling energy demand in summer is increasing by 100% or even more. And that's even true if you use heat mirror glass, low E glass called, so-called glass that has reflects the heat radiation. And that's something that goes also to the direction of how to deal with the climate change, not only to prevent it, but also how to deal with the climate change. So we are addressing both aspects of this situation. How do we want to deal with it? We want to deal with it that we have a switching and intelligent control of the radiation that goes through windows in a building. And with two strategies for it. The first strategy is electrochromic cells. How do electrochromic cells work? You can apply a voltage just by an electrical switch. You apply a small voltage, and this small voltage will result in a change of the color of the window. In particular, it will reduce the transmission from a bleach state here, 78% transmission of visible light. It will reduce the transmission of the visible light to a much lower level. The window turns dark to some degree. And then we combine these electrochromic cells with thermochromic systems. And thermochromic systems work in a different way. They switch their transmission spectrum, or they switch their radiation, or how much light they let through the window. They switch it by temperature. So as soon as the surface of a window reaches a certain temperature, 60, 50 degrees Celsius, then you will find out that it turns into a reflective state, and the transmission of the infrared radiation, so the heat radiation, is significantly reduced by a factor of 2 or more. So that is the idea. We combine a switching of the visible light transmittance with a switching of the infrared transmission. And how does it look like? For the electrochromic shading, we will see a little more about this in detail when we describe the technical solution. But let's give you an introduction or an idea of how it works. You will see that the window is slowly, gradually turning dark. You will still be able to look through the window. So it is not completely black. It's not a privacy screen. You will still be able to look through it, and you will have about 10% transmission left, visible light transmittance left. And that's just an illustration. How does it look like in practice? Here you see on the left side an electrochromic window that has been made in the Switch2Save project. So it's an isolating glass unit with 1.2 times 3.6 meters. So really for large windows and for large glass facade. And on the right side, you see an example where we just mount a thermochromic thin glass example on an existing window. The big difference is that for the thermochromic, you will not see with your eye, you will not see the difference between the infrared reflective state and the infrared transmissive state, because all changes, all switching is happening in the infrared wavelength range, really controlling the heat radiation. So what is the idea, or how do we integrate this into windows and into buildings in the Switch2Save project? We practically apply these thermochromic and electrochromic system on the plastic film for the electrochromic and on a rollable thin glass on the thermochromic. And that is something that will be laminated onto a glass pane. And this glass pane will form the outer pane of an isolating glass unit. And these insulating glass units, they are universal. You can use them for glass facades. You will use them for transparent roofs even. You can use them for smart windows. So practically, the idea is that we can replace existing windows by smart windows just by replacing the window at all and using the new energy smart solution, I would say smart window here. And what we also do in the Switch2Save project is we have two real live operational building demonstrators. This is an office building operated by Vasakronan in Sweden, in Uppsala, and this is the second largest hospital of Greece, the General Hospital of Nicaea, which is located in Athens. So we have really two different climate conditions here. We have a northern climate, and we have the hot Southern Europe climate, and we want to demonstrate here. This is something that's still happening, so that we're still in preparation. The project is aligned for 4 years, so we are now in the third year. We take the energy demand in the state-of-the-art system, how is this installed at the moment, then we will replace the windows and we will install our smart windows, and then we will monitor the energy demand for another full year. That is how the project is set up. And the overall strategy in the end to really come to a good energy saving is to implement intelligent switching protocols. So it is, for example, taking the weather conditions on the outside, taking the climate conditions, the temperature, the overall light conditions in the inside as the base for an automatic switching of the electrochromic window or the thermochromic and electrochromic combination in a roof. So that means in a winter, you will probably like to have the heat radiation from the sun going in. So then you will practically have a transmissive state. This is what you want. In summer, you want on the day, you want to have the heat radiation reflected. And the second story is that in winter at night, for example, you want to practically block that the heat inside the room is transmitted to the outside. And that is really the idea here, that we go on where we want to save energy. And in summer, really, thermochromic roofs can also help, because if you have no electrical contact there, not possibility to bring electricity or whatever, you can have a thermochromic roof that blocks the infrared, the heat radiation on a certain temperature of the surface. That's the idea. And how does it serve the energy saving of the building? We have done modelings. So this is really calculations. It's not yet measured in life. This is something we do in the third and fourth year of the project. But from modeling, we learned that with a configuration that combines electrochromic and thermochromic, even the electrochromic alone helps already a lot. And if we combine this in a window with large windows, in a building with large windows, we had an example of an office building in Athens, we can save the primary energy demand by 60%. We can reduce it by more than 60%. And practically it goes mainly towards the energy demand for the cooling. So we can reduce by a factor of 2 the energy demand for the cooling, or even more. Yeah? And we can even reduce the energy demand for lighting in a building in Athens. And how does this work? Usually, if people feel uncomfortable in the building, they use the external window blind. They practically turn off the light from outside, and they switch on artificial light that they have in their offices. And that's something that we can definitely reduce, because the electrochromic windows, they are still transparent to a certain degree, and you can switch them to an intermediate state. So that's absolutely perfect for the illumination in the building. And even in Stockholm, even in Sweden, you see that there is energy demand for cooling, and this can be reduced to almost zero, because the total saving potential is a little different here, but still beyond 30%. And this is really due to two effects. One effect is to having the smart insulating glass unit to smart window at all. And the second part is really to implement automatic switching protocols, where of course the automatic switching protocols, this is something where you have to interact with the user. Think about the thermal comfort, think about the building comfort, the overall comfort in the building. Yeah, that's two things that definitely we want to see with you, the architects, the upcoming architects, whether you can probably even top these numbers. So maybe, or at least show us how, or show yourself and use the technology to maximize the impact and to probably create building designs that have not been possible before, just because the energy balance of these glass buildings, glass palaces, is too difficult to achieve. And that's probably something where I'm curious to see what design we will be able to do with this new technology. And based on that, I want to thank you very much for your attention, for listening, just to show you all the people being partnered in Switch2Save from the university, that bringing us the technology for the Thermochromic Fraunhofer Institutes with pilot production facilities and technology development, AGL Chromogenics for the electrochromic technology, facade glass, really a maker for glass facades. Amir is here for the project management and really for the public relations activities. E2ARC architects, so here you have also a perfect person to ask if you have a question about the contest, and the building owners. NTUA, the National Technical University of Athens, who do really all the nice calculations and the building simulations and the testing. And finally, Vasakronan, office building owner in Sweden, and the hospital in Greece, Nikaia Hospital, where we will go into the children's station and into intensive care units. So really, we are speaking about a technology that you can use in a sensitive environment. Thank you very much, and I hope I was not too long.
No, you are perfect in time, John. Thank you very much for introducing the Switch2Save project in such a clear way to understand, and to also illustrate electrochromic glazing and the intelligent switching protocols. The next, the next presentation is a joint presentation about smart and switchable windows. It will be presented by two partners in the project, NTUA, which is the Technical University of Athens. They are a work package leader. The presentation will be done by Michaela Dazzi. She's a mechanical engineer that she graduated from the university. And the second speaker is Alexander Kraft, also partner in the project, but not from the research university part, but from the industry. He is, Alexander Kraft is an expert in electrochromic systems in chromogenics, as you just have seen in the presentation. He is also a work package leader in the Switch2Save project. I give the floor to Michaela, please.
Yes, thank you for the introduction. And hello, everyone. I will now share my presentation. I hope you can all see the presentation.
Yes, nice.
Yes. So this presentation is about the contribution of smart and switchable windows in energy efficiency and comfort. Firstly, if we take a look at the energy balance of a window system, depending on the temperature difference between the exterior and the interior side, heat is transmitted through a glazing system from the warmer towards the colder side. And this heat can be transmitted through conduction in the glass panes or the frame of the window, as well as convection due to the air movement on the window surface or its cavities. The outside air can also enter the interior space through infiltration from the various openings. And finally, as we all know, windows are a source of heat gain for the space due to solar radiation, which can vary depending on the location of the building, the orientation, and the season. An important metric for Windows systems is the U value, which expresses the insulation ability of a Windows system. The U value is defined as the rate of heat transfer divided by the temperature difference, and therefore a lower U value corresponds to lower heat transfer and higher insulation. The U value is highly dependent on the configuration of the Windows system. So for example, for an ordinary single glazing, the U value is quite high at approximately 5.8, while for a double glazing that has low coating and argon filling, the U value is much lower at approximately 1.1. Despite their various benefits, windows tend to be a weak point of the building envelope, as they are responsible for approximately 60% of the total thermal loss. And therefore, there is a need for windows that have lower U values to improve energy efficiency. Another important metric is the solar factor, or the G value, which is defined as the sum of the direct solar transmittance through the window, as well as the secondary heat transfer, which is the heat that is absorbed by the window and then re-emitted towards the interior. The G value is essentially the percentage of the instant solar heat gain on the window that is then converted to heat gain in the interior space. So for a colder climate or during the winter months, a higher G value is desirable to reduce the building's heating needs, while for a warmer climate or during the summer months, a lower G value is preferable to reduce the building's needs in cooling. The visible light transmittance is also an important metric. It expresses the percentage of visible light that is transmitted through the window. And obviously, it is important to have a high value for the visible light transmittance to ensure visual comfort for the occupants of the building and to also reduce the building's needs for artificial lighting. Now, regarding the impact of shading. In the absence of shading, windows allow more daylight to enter the space. This is desirable especially during the winter months to reduce the building's needs for heating and lighting. And at the same time, it increases occupant comfort since they are allowed to have visual contact with the environment of the building. However, overheating of the space can occur during the summer months, which leads to an increase in cooling needs, and there is also a risk of glare that causes discomfort. Interior or exterior shading systems are able to protect the space from overheating due to solar radiation, improving the building's energy efficiency in terms of cooling. And shading also offers protection from glare and UV radiation, and it enhances privacy. However, a shading system might obstruct the occupant's view to the outside, which might create a feeling of being closed in to the occupants. Regarding the total fenestration area and dimensions, an important metric is the window-to-wall ratio, which is defined as the ratio of the total window area divided by the exterior wall area of the building, taking into account all the exterior walls. And in this picture here, you can see the same building depicted for 3 different window-to-wall ratios, ranging from 25 to 50 and 75%. Another important aspect for windows is the ratio of height to width. Here, a higher value, which means that the height of the window is greater than the width, allows greater solar penetration in the space, but limits view to the outside, while a lower value, where the width of the window is greater than its height, allows a more uniform illumination of the space. Apart from energy efficiency, another important factor is comfort. And to better understand the impact of windows, it is important to find a way to quantify comfort, which is divided into thermal and visual comfort. Thermal comfort is defined as a state of mind in which a person is satisfied with the thermal environment and desires no further change. This can be affected by many parameters, such as the air temperature and the airspeed, the humidity of the space, and the clothing and the metabolic rate of the occupants, as well as the radiant temperature. And window operation is also greatly affected by occupant comfort. For example, during the summer, the occupants might use shading systems to keep their space cooler, while during the winter, they will tend to leave the windows unshaded to increase heat gain in the space. A popular model to quantify thermal comfort was introduced by Fanger and is based on the heat balance of the human body. This model can be used to calculate two important indices, the first being the predicted mean vote, which is the prediction of the mean vote of a large group of persons on a 7-point sensational scale that ranges from -3 to 3. -3 refers to a space that is too cold, while 3 refers to a space that is too hot, and 0 refers to a neutral thermal sensation. The PMV index can be used to calculate another index that is called the predicted percentage dissatisfied, or PPD, which is pretty much the predicted percentage of people in the space that are going to be dissatisfied with the thermal environment. And in this figure here, we can see the correlation between the PMV and the PPD indices. And it is interesting to note that even for a neutral thermal sensation with a PMV value of 0, there is still always a 5% percentage of people that are thermally dissatisfied. Another aspect of comfort is visual comfort, which refers to whether there is an adequate level and quality of illumination for visual tasks in the space. The international standards usually set specific requirements according to the space use. And for building design, an important aspect is daylight harvesting. Daylight harvesting decreases the demand for artificial lighting and is especially useful in buildings that are mainly used during the daytime, such as non-residential buildings. It has been proven that natural light is much more preferable compared to artificial light, since it improves worker satisfaction and productivity. And also, occupant comfort is improved by allowing the occupants to have a view to the outside, which reduces their fatigue and relieves them from feeling like they are being closed in. Visual comfort also includes the avoidance of glare, which is a negative sensation that can be caused by bright areas that have a sufficiently greater luminance than the luminance to which the eyes are adapted to. It can be caused by direct sunlight through a window, as you can see in the figure here, or generally by the luminous difference between a bright area and the darker task area. A glare can result in annoyance, discomfort, or loss in visual performance and visibility, and it can be quantified by a number of different indices, such as the daylight glare index. This index is calculated according to the luminance of the glare source, which in this case is the window, the background illuminance, which is the illuminance of the area surrounding the window, as well as the relative position and orientation of the occupants of the space compared to the position of the windows. Visual comfort is also affected by the color rendering index, which is a measure of the accuracy with which a light source can reproduce the color of an object when compared to a reference light source. For example, a colored window will affect the perception of the color of the objects that are on the outside. In this case, a window that has a blue tint will make the objects behind the window appear bluer than what they actually are. For windows, a color rendering of 80 or higher is considered good, and for a value of 90 or higher is considered ideal. There are many tools that we use to calculate energy efficiency and comfort. For example, Energy Plus is a free-of-cost software that can be used for whole building energy simulation. It has many capabilities such as combined heat and mass transfer modeling, and illuminance and glare calculations, and can also include an interface for co-simulation with other software. Another useful tool is Window, which includes an international glazing database of commercial glazing, as well as complex glazing and shading devices. And this software can be used to create and then import glazing systems into other software or to calculate their thermal and optical properties. For example, for a whole building energy simulation, the appropriate window systems can be first created into Window and then imported into Energy Plus for a whole year energy simulation. And this way, we are able to calculate the building's energy needs as well as the appropriate comfort indices, and we're able to improve and eventually optimize energy efficiency as well as comfort. And this is the end of the first part of my presentation.
Thank you, Michaela. This was very clear to understand how this switchable glazing works and what the effects are. Now I would like to invite Alexander with his presentation. I introduced him shortly as an expert in electrochromic systems in chromogenics, partner of the project. He is an experienced consultant with a demonstrated history of working in the building materials industry, skilled in electrochromics and other switchable glass technologies, as we are developing in the Switch2Save project. I give you the floor, Alexander.
Good morning and hello. My name is Alexander Kraft. I'm a member of the Chromogenics R&D team and the work package leader at the Switch2Save project. I will talk a little bit about dynamic sun protection glass. What are the reasons for using dynamic sun protection glass? This is an alternative to traditional mechanical sun protection solutions. You have optimum sun protection when needed. You have constant access to daylight and an unobstructed view from the inside of the building to the outside. It improves indoor comfort and energy efficiency in buildings and saves cooling energy in summer. Research shows that people feel and perform better in rooms with greater access to daylight. You have no service or maintenance cost compared to external shading solutions and the low climate and energy impact. The use of dynamic sun protection glass also contributes to building certifications such as Green Building, BREEAM, LEED, and the Swedish Miljöbyggnad. What technologies can be used for dynamic sun protection glass? We have two fields of solutions, the active field and the passive field. Starting with the active technologies, so the dynamic light transmittance can directly be influenced by the user. Technologies which are among the active technologies are electrochromic, liquid crystal technologies, and so-called suspended particle technologies. We at Chromogenics and in the Switch2Save project focus on electrochromic technology. Here, a switching of the light transmittance can be done by applying low DC voltages in the range of 1 to 3 volts. It is a slow switching, which takes several minutes. Energy is only necessary for switching, and each intermediate state between the maximum and minimum light transmittance can be adjusted. Contrary to this, liquid crystal technologies and suspended particle technologies are switched by the application of higher voltages. These are AC voltages between around 60 to 110 volts. It is a fast switching in seconds, but energy is necessary to maintain one of the transmittance state. Usually you have only two states, on, off, and without a voltage you have either the milky or a dark state, and with voltage you have a clear state or the state with a high visible light transmittance. The passive technologies, which cannot directly be influenced by the user, are thermochromic and photochromic technology. In Switch2Save, we focus on thermochromic. With thermochromic technology, switching is due to changing temperature. A gradual switching or a switching at a certain temperature are possible. It depends on the material which you use. And in the photochromic technology, the switching is triggered by incident UV light. So Chromogenics is an electrochromics company. So the question is, what is electrochromism? It is the reversible electrochemical reduction and oxidation of compounds. This leads to a large change of their optical properties. So compounds have to be chosen, which have in different oxidation states, different optical properties. To make this usable in the practice in a window, usually a 5-layer stack is constructed. This is a transparent electrode, a first electrochromic film, a polymer electrolyte, a second electrochromic film or ion storage film, and a second transparent electrode. The low DC voltage is applied between the transparent electrodes, and this 5-layer stack is packed between 2 transparent substrates, mostly glass, but transparent polymers can also be used. Here you see an example of electrochromic glass, dynamic sun protection glass, realized by electrochromism in the entrance area of a building. High light transmittance, lower light transmittance. By applying low DC voltages to the transparent electrodes, the light transmittance of the devices can be changed. In one polarity, the electrochromic devices become darker, and by reversing the polarity, the light transmittance increases. And if we cut off the voltage, when the light transmittance stays in the state it had at this very moment. Shortly, a few words to the company Chromogenics. We are a Swedish company. The company was founded in Uppsala in 2003. We are proud to be innovation leadership for 20 years. The research we bring to real products on the market is from the Ångström Laboratory of Uppsala University. We focus on smart glass, solar control, and electrochromic material. And our company is noted on the Nasdaq First North Growth Market in Stockholm. Chromogenics product is called Convalite. It is a lightweight electrochromic foil. So the 5-layer stack is placed between 2 thin polyester films, each about 100 micrometer thick. And this is very advantageous because this can be produced in a roll-to-roll technology with very low cost and high-speed manufacturing. In addition, such a lightweight, thin electrochromic foil can be transported to anywhere in the world with low costs because you do not have to transport heavy glass. In the end, this foil has to be laminated between 2 glass panes to make it durable, and the end product is a laminated glass or an insulating glass unit with 2, 3, or 4 glass panes and this laminated glass. An electronic control unit automatically regulates the tone of the film and the solar transmission, for example, by connecting to a sensor network. Also, a fully self-sustaining dynamic glass powered by solar cells, which are integrated in the window frame, is possible and is a product of Chromogenics. Here you see the optical properties of the Convalite 65 EC foil. The white part of the spectrum, this is the transmittance versus wavelength. The white part here is the UV light, ultraviolet. The yellow is the visible light. So this is what we can see. And the near infrared, the orange part, is the heat radiation. We have a high light transmittance in the bleached state and a much lower light transmittance in the colored state, and we can adjust all light transmittances in between. In the next slide, you see a few data of this product. And as a single glazed, double glazed, or triple glazed product, you can see that the light transmittance changes between 66 and 17% if a single glazed product is used. In a modern triple glazing IGU, the light transmittance can be changed between 54 and 14%. We have very good color rendering index. And of course, the U value goes massively down if you use double or even triple pane windows. Here are the colors. So the color in transmission in clear state is slightly yellowish brownish. The color in the dark state is neutral gray. And the colors in reflection, the clear state, in the dark state, are also more brownish. This is one of the disadvantages of the current state of the art of chromogenics glass, because this yellow brownish color is not very favorable. Many customers do not like this color. So one task of the Switch2Save project is to get rid of this yellow brownish color. In addition, we want to have a higher light transmittance in the bleach state, more than 75%, and a lower light transmittance in the dark state, less than 10%. This would massively improve the properties, the performance of the glass, and also the user acceptance. These are two examples of our glass. This is the single glass. On the left side, you see the bleaching of the glass. And on the right side, you will see the coloring of the glass. This is faster than in reality. As I already said, it takes a few minutes, and here it only takes a few seconds. But of course, in such a presentation, we cannot wait minutes for the glass to change light transmittance. Yeah, these are real objects. And here, shortly, a few words to the production process. As I already said, we have a roll-to-roll technology. Two plastic foils are coated with electrochromic films, tungsten oxide, nickel oxide, and then laminated together with a polymer electrolyte, and then you have the EC foil on rolls. The end product is the Converlite dynamic electrochromic IGU with 2 to 4 glass panes. We have a freedom of design, so not only rectangular shapes are possible, but also circular or any shape, triangular, curved. Maximum dimensions which can be produced at the moment are 1.5 meter times 4.4 meter. Maybe even 5 meters is possible here. And everything is automatically controlled via control system. A few examples of projects we have already realized. This is a residential building in Uppsala called Knäckepilen. And here, these windows are all equipped with electrochromic glass. You see the slightly yellowish color, which shall be removed in the Switch2Save project as one of the goals. This is a hotel in Bergen in Norway, Scandic Hotel. Here we have 230 square meters of dynamic sun protection glass installed. This is the office in Sortland, Norway. Here, these offices are equipped also with about 240 square meter electrochromic glass. You also see the slightly yellowish color. This is another office of the company Shimano in Uppsala in Sweden. Here we have 230 square meters of electrochromic glass. This is the roof of a school in Göteborg in Sweden, 520 square meter Converlite glass. And this is the project we are equipping at the moment with the electrochromic glass. It's the GT5 project in Oslo in Norway. So here everything will be equipped with electrochromic glass, still with the brownish colored glass. This is the largest project we had so far. It's 1,800 square meters of Converlite dynamic sun protection glass. Yeah, only a few words to switching protocols for the electrochromic films, which are possible. One possibility is, of course, manual control according to the user. So each user in his office room or in his apartment can manually switch the device as he wants. We can have a predefined control according to a specific schedule. Maybe in the night, in the early morning, and in the evening, we have clear glass, and over the day, we have dark glass. And the most advanced is automatic control, taking into account data from sensors, daylight sensor, light intensity sensors, radiation or temperature sensors, and use a predefined algorithm to change the light transmittance of the glass. Here you can see that with what I already said, that different states are possible. Yeah, this was my part for the Switch2Save project, and I want to thank you.
thank you, Alexander, for the very interesting introduction to electrochromic glazing, the glazing that you are producing with your company Chromogenics, partner in the project. Also, the examples were very interesting, and important for us architects is to see and to know and to understand how it looks like, this glazing that changes color. Because yes, for the design projects, is also very important. Now we come at the moment of launching the architectural design competition. I did not yet introduce myself. My name is Sarah van Rompuy. I'm an architect.
Sarah.
Yes.
Sarah, excuse me. There is a presentation left from NTUA, the second part.
Oh, sorry, yeah. Sorry. Yes. Okay. Yes. So it's Michaela again then.
Yes. And this part is much shorter than the previous one. So, as Alexander previously mentioned, another type of dynamic glazing are thermochromic windows, whose optical properties change depending on the temperature of the thermochromic layer. Thermochromic windows are passive systems, meaning that no power supply is required for their operation. In the frame of the Switch2Save project, thermochromic cells have been developed on ultra-thin glass in rolls of 300 millimeters width up to approximately 15 meters length, with a total thickness of only 0.1 millimeters. In this figure here, you can see the transmittance of a thermochromic sample that has been developed for various wavelengths. And you can see the transmittance for temperatures under the transition temperature, which in this case is 21 degrees, and for temperatures higher than the transition temperature. And this darker green area here corresponds to the visible spectrum, which is the light that we can see. So we can notice that switching of the thermochromic layer leads to a significant reduction in the infrared transmittance, while the transmittance in the visible spectrum is not affected. And here you can also see some characteristic optical properties of the developed thermochromic samples. In this figure, again, you can see how the exterior environment can be seen through a thermochromic sample compared to a normal window. And here you can also see a visual representation of the color of the thermochromic samples in transmission, so as seen from the interior of the building, and also in reflection as seen from the outside of the building. And here it should also be noted that because the change in the sample's properties in the visible spectrum is not significant when it is switched from the cold temperature to the higher temperature state, these colors also don't change significantly. The aim of the Switch2Save project is to combine in the same insulated glazing unit both an electrochromic and a thermochromic film. And in this configuration, the electrochromic film will be responsible for reducing the transmittance in both the infrared and the visible spectrum, while the thermochromic film will only further reduce the infrared heat transfer. Here you can see a visible representation of the system that we aim to create. And here again, you can see a representation of the color of a combined electrochromic and thermochromic system. Here is the color as seen from the building interior for the clear state of both films and for the dark state of both films. And here is the color as seen from the outside, again for the clear state and for the dark state. Now, two indicative case studies that were conducted in the frame of the Switch2Save project will be shortly presented. The first one refers to the neonatal intensive care unit of the General Hospital of Nikia in Athens. Here you can see the building model that we created for the clinic. And in this study, we examined various control strategies for the electrochromic film of a combined electrochromic and thermochromic system. And we calculated the energy needs of the clinic for heating, cooling, and lighting for the different control strategies and compared them to the current state of the clinic. It has double windows with interior shades and exterior awnings. And the results showed that it can be a reduction of approximately 11% in primary energy use using the Switch2Save insulated glazing units. And there can also be an additional reduction up to 1.8% when implementing optimized switching protocols. At the same time, the visual comfort for the people in the clinic is significantly improved since more daylight is allowed in the space, and the people are now able to have a view to the outside, which was previously obstructed by both the interior shades and the exterior awnings. And the second and final case study refers to the Business College of Athens in Greece. This is an office and educational building that has a fully glazed south facade that is shaded by exterior overhangs as well as interior shades. And the study showed that replacing the current double windows with triple electrochromic windows leads to a significant reduction between 21 and 23% in primary energy use, depending on the control strategy. And at the same time, visual comfort is also improved. Here in these two sets of contour plots, we can see the daylight distribution for two characteristic zones of the building on the south facade and on the north facade. And in each set of contour plots, the contour plot on the left refers to the case of the interior shade, and on the right to the case of the electrochromic windows. And here we can see that the electrochromic windows allow a much more desirable daylight distribution in the space, securing illuminances in the desirable range between 300 and 3000 lux for most of the space, and under illumination that was presented in the case of the interior shades is also avoided. And finally, the occupants are again able to have a visual contact with the building's environment all the time, whereas in the case of the interior shades, this is obstructed when the shades are closed. Thank you very much for your attention.
Thank you, Michaela. Again, very interesting. I would like to ask if there are any questions. Please raise your hand or even speak. No questions yet. We will have another moment after the launch of the competition for questions. So finally, it's the moment to launch the competition. We have had all the technical details about this wonderful smart glazing. And I will share a presentation with some inspiring examples and what you have to do to submit a project. Do you see the presentation?
Yes, we can.
Okay. So today is the day of the launch with all the information. I will start with some examples to inspire you. And I really wanted to start with an existing building, because if we think of new developments, we think of new built architecture. This building, you might know, it's the Gare Maritime in Brussels. It was built in 1907 as a train station, a depot, in fact, and it now is renovated towards an energy neutral building. You see with the big glass parts what value this gives, how inspiring this can be. In this building, it will be energy neutral. There will be no fossil energy anymore. Heating and cooling will be produced with geothermics, and the electricity will be produced thanks to photovoltaics. Of course, the original building had single glazing, but this renovated Gare Maritime will have triple insulating and smart dynamic glazing. And all this without touching heritage values. Some more examples about extensions of a building completely in glass. This building in Tallinn by Coco Architects, where the main functions of glass are allowing daylight into buildings, ensuring a visual connection with the exterior. Of course, you can have the glass facade in to express or to give a contrast between new and old. Another example we probably all know, Zaha Hadid in Baku, to show the clarity and the aesthetic nature of glazing. It is unmatched. This building, the Antwerp Law Court by Richard Rogers, also shows that glazing has many forms, types, and applications, roof, vertical, horizontal, to enhance the architectural value of a building. This project in Milano by Bjarke Engels from Big Architects illustrates that the use of glass in architecture has really increased over the last few decades. It's now really a major expression. It's a design element in commercial office buildings, airport terminals, train stations, shopping centers. And this building in Milan really illustrates this. So if we use glass as this expression, really, there is a key role for the glazing selection. When we use glass as such a dominant facade feature, the choice of the glass is key. Because in modern buildings, up to more than 60% of energy transfer goes through the building envelope is related to the glazing components. You probably know this building. This is the Hamburg Opera House by Herzog and de Meuron. What is the challenge? In this example, I would like to show the challenge, the importance of an energy saving strategy. This is the latest architectural jewel in Antwerp, the Port House, designed by Zaha Hadid. It was built, as you can see very well, on top of an old building. It's an old fire station. And this innovative building has its roots in the past. It's the new headquarters now of the Antwerp Port Authority. 500 people are working there. And it's a symbol now of the growth of the Port of Antwerp. And I'm sure there is a good energy strategy here because it wouldn't be possible otherwise. But I'm still wondering which of the two buildings would be the most energy efficient and sustainable. The old fire station with the small windows dating from 1922, or the new glass diamond from 2016. The energy saving strategy. There are several ways to think about energy saving and controlling the sun. With careful consideration of the orientation and the use of exterior shading, the integration of large transparent facade and roof elements can become an integral part of the strategy. So here you see in this building in Ghent, the architecture, in fact, is a way to protect the large glass parts from the sun. Here they use this as a way of expressing, but of course, if you look from the inside, it can compromise daylight conditions, and it can also block the view to the exterior, as you see very well here in this interior view of the library in Ghent. So what is the answer to these challenges? As we learned from previous presentations, the answer to the challenges can be high-performance glazing. This example was also in the presentation of Alexander Kraft, because this is the glass we are developing in the project. The high-performance glazing can contribute to the insulation of a building and deliver energy savings while ensuring comfort conditions without losing site and architectural freedom. Another example, why would we use this smart and switchable glazing? Because the glass has no limitations, which gives indeed more architectural freedom. The electrochromic technology in the dynamic solar control glass, it stops the solar heat even before it enters the building. It can block up to 90% of the heat and isolates as good as a wall. That's important, that you can have your glass parts having the same insulation grade as the wall, by still providing daylight and a good view. It also acts as an automatic climate system where unwanted solar heat radiation decreases, which keeps the premises cool, and the use of external solar control can be avoided. As a result, this building shows it, smart and switchable glazing is very cost-effective for all buildings. Another nice example why we could use this smart and switchable glazing, because it provides an enjoyable and healthy indoor climate that increases the well-being of people who are present in the building through daylight transmittance, ultraviolet protection, open views, comfortable temperature, and as already said, it acts as an automatic climate system where unwanted solar heat radiation decreases and the indoor comfort can be controlled. Now we go again to this building in Brussels, the Gare Maritime. And I want to show you, I think it's a very good example how it works in reality, this switchable glazing. You can see very well here how with the push on the button, the properties of the glass parts change. It renders from clear to tinted. And for the real estate developer Extensa, there were three benefits of this automated dimmable electrochromic solar control glazing. It's very easy to use. Just one switch, push on the button. And then two, for him, the avoidance of disruptive solar control elements on the historic facade. This is also really an advantage, because for a historic building, really, it's not possible to put any elements outside. And here also, this is integrated in a circular economy concept. This whole site, Tour and Taxis in Brussels, is a work in progress, and it's already compared now with the Hamburg Haven City. It will be a center point of a very exciting urban development. Then we come to the Switch2Save opportunity, the glass we are developing in our project. This image we have already seen before, but this shows how the color from inside can go from very clear to darker and darker blue. This is the window the Switch2Save project is developing. So you see here on the detail, it's a triple glazing with an electrochromic film and an thermochromic film inside. But we have seen in the other presentations how this was produced. Now we come to the Switch2Save design competition. This competition aims to collect design concepts of non-residential buildings featuring glass facades, roof, large windows to wall areas in any climatic context. What would we like to receive? A design concept. It doesn't have to be a building which is already built, just a concept. It has to be non-residential. There is no other restriction regarding size, location, or use of the building concept. It can be on any hypothetical site, any size, and it can be in the city, on the countryside, anywhere in Europe, in any climate. The eligibility, who can participate in this competition? We really wanted to target students and young architects. Young architects up to 5 years of diploma, or else a team of architects, physicists, engineers led by an architect, and they have to be enrolled in an academic program, bachelor, master, etc. There is a limit when you work in a team. There is a limit of 3 members per team. The competition is open to all nationalities, but the team members should be based in Europe or one of the associated countries like Switzerland, Norway. We really target students and young architects because we know they are working in the master program on big projects which will be very contemporary with big glass parts, and we think that they will develop projects that will be fit to participate in this competition. What are the evaluation criteria? We have 4. The design concept and the level of innovation. We will ask you to elaborate your design concept, think about drivers, possible barriers, other parameters like aesthetic integration, of course, leading to the proposed design as a response to the competition brief. We will ask you to elaborate your energy saving concept, to describe how your project addresses the need for energy efficiency in view, of course, of the European energy targets, and how the design maximizes the energy saving potential of the electrochromic and thermochromic glazing. We also would like you to show the exploitation of the Switch2Save smart functionalities and to show the replicability of your concept, and also to tell us about the user comfort in the building you have designed. In the jury, we have a balanced jury with 2 persons from research, John Faulte and Maria Faulte. Maria Faulte is professor at the Technical University of Athens. And then we have Alexander Kraft and Hans Swart, 2 partners from the project, and they are from the industry. And there will be 2 architects. One of the 2 is me. And the next one, but he did not give his approval yet. It's a member of the external advisory board, an architect from Milan. What can you get from it, from participating? We have monetary prizes. First prize, €1,000. A second prize, 500. Both awardees, they get a demo kit of a window, a real window. They are invited to present the winning project at the prize ceremony. The travel expenses are covered, and this will be most likely organized in combination with the visit of one of the demo buildings in Athens or Sweden. We can also offer an internship at the Technical University of Athens. And of course, there will be the media coverage. So what to submit? We don't want to make it too complicated. We want to make it easy for you. We would ask one PDF file, maximum 30 megabytes, with a brief description following the submission brief template. We also would like one infographic, one big panel presenting the proposed design in response to the competition brief. And then, of course, you are also free to add other visual material, photos, plans, anything which illustrates your design. And you have to sign a declaration of authorship, of course. How to submit? It will be easy. You will registration through a link where on the website we will ask name of team leader, the several team members, your status of if you are an architect or a young architect or a student. The young architects can be up to 5 years after the diploma. This is how we define this. You will get confirmation of your registration by email, including information on a username and a login, and a link to the OwnCloud folder. Then comes the time that you submit your proposal to the OwnCloud, and you will get a confirmation again. And then finally in September, you will be informed on the final results. This is the schedule. So we are now launching 28th of February. The deadline for registration is 31st of May. Submission deadline is 31st of July. Why did we take end of July? Because we know that students are handing in their final master project in May, June in most universities and architecture schools. And then they have some more weeks to prepare the documents that are requested for this competition. And then finally, after the summer, by the end of September, the winners will be announced and we will organize the award ceremony. Now, there is only one thing for me to wish you good luck and thank you for your attention.
Yeah, also from my coordinator side, I would like to say good luck and maximum success. And we're curious to see what type of interesting designs we will see and are possible with our systems.
Thank you, John. Now we will ask for another time. If there are any questions, now that we have had all the information from the people attending this training event.
Can a speaker ask a question?
Yeah.
Yes, of course.
First a comment. As you can see, I stayed for the whole meeting because I think it was really interesting. And as ECTP president, it's also important to get to know better some of the projects. And so I really enjoyed it. You know that I'm also leading an action cluster in the Smart Cities Marketplace. So eventually we could present Switch2Save at one of the Smart Cities events. So I would like to propose you that. Second, in reference to the comments I made earlier, it would be interesting to also know about the life cycle assessment of the solutions, whatever happens upstream before the solution is available, and in case of deconstruction, what is planned to happen. These aspects of circularity are important more and more at the EU level. And also good luck to the people who will participate to the competition. And Sarah, there is a deal. I want to visit the Gare Maritime in Brussels into a taxi. I want to go and visit that building as soon as possible.
Wow.
Well, thank you. Thanks to all of you. Thank you.
Paul,
Thank you, Paul.
very much for the question. Maybe I step in to answer the question about the life cycle assessment. We are doing this. The activities have started. Of course, it makes sense to do it with the materials selected and with the components selected. So this is really the third and to some degree the fourth year of the project. And yeah, we are happy to present the results as soon as possible. Definitely, it's part of the story. And also, we are really happy to look at these smart cities projects and to look at these smart cities events, because the technology that we have in Switch2Save, we use it now with electrochromic and thermochromic system, but we really can expand most of the things with photovoltaic, with energy storage, with energy supply. Yeah, so this is really something where I'm looking at this.
Thanks very much. Thank you. Perfect.
So I'm waiting for a suggestion for an event from you, and then we can go.
I will tell you, we don't have a date for the moment for the next meeting. As soon as we have a date, we can plan something.
Perfect. Thank you.
Okay, interesting. Are there any more questions from speakers or other participants? No? Then I think we are really perfect in time to close this training event. As I told you already, the presentations will be available on the website, and I'm sure students or architects who want to participate will come back to this and to see the technical details and the details for the competition. Thank you to all the speakers.
Thank you also from my side to everyone, and Sarah for preparing all these things, and to Paul for coming, and stay in touch and see how many, hopefully a lot, applications we will see.
Thank you.
Thanks to all of you. Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.